Hi, in this presentation, we're going to talk about our cardiovascular engineering project based on valvular heart disease. Throughout this presentation, we're going to talk about the main objective, the methodology we used, the discussion we had, and the results we obtained. Also, the conclusion with the important findings that we had. As we have mentioned before, our main topic is valvular heart disease, but for this project we're going to specifically talk about mitral valve malfunction, which is a common cardiovascular issue. The mitral valve is located between the left atrium and the left ventricle. We define our main objective of the project as the design and development of different arrangements of a cage valve heart valve using the software SolidWorks, so we could determine the best design that would reduce flow-induced thrombogenicity for this type of disease.
As part of our work, a 3D model of the left part of the heart according to human anatomy was performed, as well as a model of the conventional valve caged according to standard values. This model was analyzed with 3 different designs for the cross-section of the struts: circles, squares, and ellipses. The square struts were made using dimensions of 0.45 by 0.45 mm, the circle struts with a diameter of 0.4 mm, and the ellipse struts with dimensions of 0.45 by 0.35. For the CFD, 2 leads were created, one on the mitral valve and the other on the aortic valve. At the inlet, a flow of 1.26 times 10 to the minus 4 was defined, and at the outlet a pressure of 799.80 pascals was established. In the finite element analysis, the struts were tested with pressures from 10 to 160 millimeters of mercury that were applied to the valve wall.
Now we're going to present a discussion on the results of our main project. First of all, we need to address the main objective or issue that focus our project. Mechanical valves are often implemented or are mainly used because of how long can they last within our heart. However, one of the main problems that it causes is thrombosis due to 3 main factors. There are material properties, shear stress, and areas of abnormal flow. The material properties refers to low biocompatibility of the material chosen to create the valve. This low biocompatibility reacts with blood cells or cardiac muscle. They triggers the immune system and a clot is formed. The shear stress refers to high stresses that damage blood cells and they can form a clot too. And areas of abnormal flow means that they can generate extra pressure over the cardiac muscle, forming a clot as well. We decided to focus on these 2 last causes, the shear stress and areas of abnormal flow, in order to generate our parameters that we are going to analyze within the project, that are an hemodynamic analysis referring mainly to blood flow, pressure, and velocity, a maximum stress, that is the stress experienced by the valve, and the surface area, which refers to the overall surface the valve fills. We implemented 2 types of analysis: a computer fluid dynamics analysis and the finite element analysis. The CFD analysis we mainly uses to obtain the bloodstream velocity and also to obtain the pressure in each strut. And the finite element analysis we implemented to obtain the pressure bearing capacity, which refers to the stress experienced by each strut. In order to obtain the velocity, a new plane was created parallel to the cage valve. This approximation will make it easier to determine the velocity after the blood flow passes the valve. Here we have the evidence of the circle strut the velocity calculated, the velocity calculated in the ellipse strut, and the velocity calculated in the square strut. In order to evaluate pressure, a surface plot was created, and using the probe tool, an individual point was selected. We selected the tip or the top of the strut, which is the one that felt the more pressure. Here we have the evidence for the circle strut, the ellipse strut, and the square strut. Here we have a table of results, and here we can see that the velocity remained constant within each of the designs. Therefore, we can infer that the design of the strut does not affect the blood flow. Also, as we can see, the pressure only varies in 2 Pascal from each of the designs. So we can also conclude that the design of the strut does not influence the pressure exerted on the valve. Therefore, by analyzing these results, we can conclude that by changing the design of the struts, we do not get to change or reduce the areas of abnormal flow that are caused within the bloodstream. As we can see from the flow simulation presented in the figure, we can see several areas of abnormal flow caused, and by changing the design of the struts, we can now reduce them. The only thing that may affect directly the blood flow is the valve in the cage wall valve. On the finite element analysis, all elements were fixed except of the valve, since it is the main precursor or agent that is exerting the pressure over the struts. The struts were tested with pressures that goes from 10 millimeters of mercury to 160 millimeters of mercury. These values represent the diastolic and systolic cycles, and this analysis makes it easier to distinguish which design can withstand more pressure and in which area the stress is exerted, as we can see from the picture that is at the tip of the strut. Here we also have a table of the finite element analysis results. Here we can see that the stress changes within each design and also at different levels of pressure. The differences are quite noticeable, as we can see from 10 millimeters of mercury and 160 millimeters of mercury. The one that generates more stress is the ellipse strut stress. After that, we proceeded to plot this pressure against the stress of each design of strut, and the graph shows that the circular strut cage ball valve has a higher pressure bearing capacity relative to the others, since less stress is experienced at higher pressures. Therefore, this design does not harm blood cells by exerting less stress over them. As we can see from the graph, the circle generate less stress at higher pressures. Therefore, they are less likely to harm blood cells, reducing the risk of thrombosis generated by the mechanical valve.
Taking into account the results of the flow simulation analysis of the left human heart with cage wall mitral valve and finite element analysis indicates that circular strut has superior design compared to square and elliptical struts. Therefore, this optimization of the structure of the cage wall valve would greatly reduce flow-induced thrombogenicity.